Good evening, everyone. We apologize for the delay that happened. We did not foresee this. So, we are glad to welcome you to another student's talk given by Sreedev, a fifth year BSMS student. Uh, he is currently working with Professor Rukmini Dey at ICTS Bangalore. His research interests are in differential geometry and the study of minimal surfaces. Today he will talk about his research work and the story of how he solved an open problem. So now the stage is yours. You can start.
Thank you here. So so I have a incredible connection with giving math club talks. I have a incredible connection with giving math club talks in the sense that I gave my first talk in June. Just a second, I forgot the talk. So I gave my first talk in June, and it was titled "Shapes of Soft Films." And a few months after that, I had the pleasure of submitting my first article on Arka. Then I was invited to do another talk by Maths Club. This time invited. The first time I asked them to give, can you give arrange a talk for me? Yeah, and this time I gave a talk. It was titled Math with Pictures. And a few weeks after that, I got to submit my second article. Now, today I am standing in front of you with this talk, and I'm also giving you free tea and coffee for attending, which people don't normally do. Yeah,
Is there any of it after the talk?
no, I can personally give it to you, but I don't think the MDP guy would. Maybe we can. We will try to argue, but so here we are giving you free tea and coffee, and you are seeing a pattern. Months became weeks, and what's going to happen next? So to you, I present it to you. Tomorrow, I'm going to submit my third paper. And now I have to be the bad guy and tell you that it's not happening. So, I just made it up just to see how people react. But keep an eye on the archive because if you keep on looking for tomorrow, by the end of March you would see a table. Yes. So, now let's get into the heart of the matter, which is to tell you a story of how we solved an open problem. So what are we going to do in this talk is that we are going to time travel. It would be like the movie Memento, if I'm not pronouncing it wrongly. So what we are going to do, we are going to go into the past, what I did as a younger self, and then we are going to sometimes switch between past and future. But unlike the movie, there won't be any color changes. So it would be just like that. I would be going through the past, then I would go through the future, and you would see some connections, relationships, and it would be like an HSS talk, but with some math here. So, so let's get into the heart of the matter. Because before that, I had to thank the people involved. And I first want to thank my advisor, who is one of the kindest and smartest people I have ever met in my entire life. And you would see some shades of how it is like to work with her in this talk. And then I have to thank my wonderful friend Arka from IISC Bangalore, who I had the pleasure of meeting during this project. And he's again one of the insanely smart and most annoyingly smart people who you would ever met on the planet. So you would again see what it is like to work with him in this talk. So now let's go to how it all started. So I learned the basic theory of minimal surfaces after the first talk which I gave in June. And then I was supposed to, like my supervisor said, listen Sreedev, let's go solve an open problem. So what happened is that she sent me a book and she told me to read it. So this is a physics book by Vita, and let me show you what she wanted me to read. So this is a page, and I want you to notice two things. First of all, we are in page number 680. So my supervisor was confident that I would skip 600 pages of a physics book without taking any physics courses in my last 2 years of my BSMS and understand everything perfectly. The second thing is that everything here is based on PDEs, and I was too scared of PDEs to a point where I didn't even took a PDE course. So I understood absolutely nothing from this assignment. And if you, yeah, PDE means partial differential equation, like someone pointed out. So yeah, if you are a nice mathematician, now your job is to look at a PDE book and you would study that book and you would try to understand this thing, right? So that's the way a nice people would go. But I wasn't a nice mathematician. So what I did is that I asked for an appointment so that my supervisor could tell me what exactly she wanted me to do. So I asked for an appointment and she agreed. And then the meeting happened. So let me tell you what happened in the meeting. So in the meeting, she wrote this equation down. This is a partial differential equation known as minimal surface equation. Then she changed a few signs and she got another PDE, a partial differential equation. Both have different names, but they look identical. Okay, now what she did is that she picked a geometric problem. So this is a particular parameterization that minimal surfaces have the solution to the first partial differential equation, and everything here is controlled by complex analysis in the sense that all functions are complex valued and everything you are taking real parts and so on. So what did she do next? Then she showed me something similar for the second PD. So you see that here everything is controlled by real analysis and the functions are real valued and the integrals are normal real integrals. So there is something happening here. So then she picked another geometry problem, which was this, which is known as the Buerling representation formula, and it is for minimal surfaces. And then she showed me the analog of it for Bonnet resultants. This is the analog of it, which was known at that time. So we are the ones who proved what the analog is, but you can guess what the analog should be from here because there is a that integral would become a real integral, and there won't be any real parts. Every function would be real valued and so on. So that was what we expected. We were excited, and that's my way of conveying the excitement. Now, so what happened next? So I have to work on this problem. Now, I understand that not every one of you had done 1 month of minimal surface theory. So let me go back and explain to you what happened in the first equation, like how did it came. So what is minimal surface Buerling problem? Before that, let me credit the person who came up with this thing. So this is Buerling, Immanuel Buerling, and these are pictures of Buerling with and without a beard, which I got from Google. Now, let's get into the heart of the matter, which is to explain to you what Buerling problem is. So you can take a wireframe like this, you can dip it in a soap solution, and you would get a particular field. There is nothing special about this loop. You can take a complicated shape, and you can ask what would the shape of my field input be. Okay? And your job is to guess the shape based on the geometry of the loop. Okay? So some algorithm kind of thing. That's the problem. And you try to make it abstract. So you draw some axis and then you try to solve this problem. But after a few minutes of working on it, you would realize that there is an issue with this problem because I could have also taken a single circle and dip it in a soft solution. That would give me a surface containing this power circle. But I can also do this where I attach an upper circle with it and then I dip it, then I would get a different surface. So there are exactly at least two surfaces which contains the same curve. So there is no notion of uniqueness in this problem. And as mathematicians, we love uniqueness and we want to somehow give a aspect of uniqueness to it. So how do we give uniqueness to this problem? Well, one can introduce the aspect of uniqueness by introducing tangent planes. So one can say that my tangent planes, when you dip it at the soap solution and get it back, you want the tangent planes to be arranged this way. So you specify the arrangement of the tangent planes along the loop and you want that arrangement to happen. So this is a way of making it unique. Okay, this is a wonderful way. But the issue with that is that mathematicians are lazy and we don't want to write down the equations of a plane at every point. So you want to simplify it. How do one simplify it? Well, you notice that every plane is specified by its normal, and normal need only one equation. So you draw the normals, and you have normals at every point. So now the problem is clear. You are given a curve, you are given a normal, you dip it, and you want a surface such that the tangent planes are arranged this way. This is all there is. The guy who solved it is Hermann Schwarz, a German mathematician. And as you can see, he have a beard. And now, this was his idea. He wrote it down formally like this. And then he tried to solve it. So as you can see, along the x-axis, it matches with the curve. The surface matches with the curve. So the derivative of the surface along x-axis should match with the curve's derivative. That's evident. And the surface normal is given to us. From there you can back calculate x2. And he got this far. And from these two data, he was able to either guess or back calculate, which I'm not sure about. But somehow he got the surface. And I'm going to show you how he got the surface. So he of course used some complex analysis techniques. And this is how he showed the surface. So as you can see, this is my way of giving a proof in a presentation, which is to tell you that God said this thing, and that is why it is true. So I'm not going to explain the proof in this talk because it's not relevant to our problem, and I see no way of using this proof in solution of the problem. But don't take my word for it because any one of you can go ahead and read this proof and tailor a similar proof for that case. We couldn't do it, and just because we couldn't do it doesn't mean that nobody can do it. Now, how did I approach the problem? So yeah, let's go back to the story and let's ask like how can we use it. So I started with the same thing, and now I am asking like how I can use it. So I started where Hermann Schwarz started, and then I took derivatives and so on. I tried to be smart. So what did I do? I took the derivatives and so on. The surfaces are controlled by real analysis. So you would expect ODEs to come, and you use theorems about ODEs, like your functions are smooth and there is a solution and things like that. Nothing was working out, and I had to do the most obvious thing, which was to agree with my supervisor and take the route she suggested. So I took the route she suggested, which was to calculate the surface normal. Now you might be wondering that if there was such a simpler suggestion there, why wouldn't I take that route? Well, that's because I thought I was extremely smart and I don't have to calculate stuff. But in the end, I had to do it, and I started doing it quite reluctantly after 3 to 4 hours. And I started calculating it. So you calculate the derivatives, nothing happens, and you calculate the normal, and then magic happens. So what's the magic? Well, even though the derivatives contains fng, there is no fng in the normal. What does this mean? Well, the surface geometry is controlled by fng, the functions fng. And regardless of the functions fng I take, regardless of how the surface looks, all of them have the same normal. So it's a crazy beautiful result. And it's a crazy beautiful result, wonderful result which you can submit in a paper. But not only that, it solves my problem. So how does it solve my problem? Well, it solves my problem because I know the normal vector field is this thing, regardless of fng. So all I have to do to find a normal for which there is no solution is to pick a normal different from this. I just pick the constant normal vector field, as simple as that. And for that normal, regardless of the curve you pick, there is no solution. So I answered my supervisor's question. I was incredibly proud over the moon. I planned to solve Riemann hypothesis remaining 11 months of my project. And not 11 months, 11 months and 2 weeks, I believe. Now what happened? So I got an invitation from Rukmini to, I have to explain in the email. So I sent this to Rukmini and I wanted to stare at the email. Why? Because even though I was sure that I almost solved the problem, I said I did some computation and it looks like. So you can see how insecure I was during that time. And I said it looks like, and not only that, I said it looks like. Please let me know if I made any mistakes. So even though I was 120% certain that my calculations are all correct and perfect, I wrote an email like this, and you would see as this talk goes on, I get more and more cocky and more confident. So, yeah. So this was my first email. This is how my first solution looked like. And then I went to ICTS. So this is what Arka said. And to be honest, I didn't really wanted to say this, but let me say this anyway. So he said it's an interesting observation, which is great, right? You look at the second line. What he's saying is that you can find maybe we can find a different parameterization where the problem can be solved. First of all, I was over the mood that I almost solved the problem. And he's saying that there is another way to do it, which doesn't go well. Secondly, it was a hit to my ego, but the secondly, he is saying something absolutely ridiculous. In the sense that if you parameterize it differently, there is no way the normal is doing this. You take a sphere, there is exactly one unit normal vector field. No matter how I parameterize, a vector which is not normal to it won't become normal to it once I reparameterize. It's a simple geometry thing which every 4-year-old knows. But unfortunately, this person didn't know it. I wanted to write back, what the hell are you smoking? I didn't do it at that time because he's from IISC and he must be smart. And to be honest, looking back, he was correct, okay? Like, he was right, but for a different reason. I'm not going to tell you that reason because I have too much of ego. But yeah, you can read his paper. Like, he didn't mention it in his paper either, but the reason is maybe I shouldn't spoil it. You will see later in this talk what the reason was. Now she said she would have a look. And then I got the invitation to ICTS, and you would see that she is taking all my charges. And looking back, it's wonderful that she's taking all my charges. But my younger self, when we are time traveling, my younger self was thinking that now I have to do some work. Like she basically paid for me before going in there, and if I don't show some work, then it's going to be absolutely ridiculous because I had to give some money back. And I don't know what I was going to do, and I had the biggest imposter syndrome of my life going in there. And then as soon as I went there, we had our first meeting, and this is a picture which is taken from that meeting, which looks like this. So if you can't see it up from the back, I am the big bird in this story. So I was thinking like I am sitting with two smartest people in the universe, and I am not able to understand anything they are speaking. And they were, of course, quoting my result as like Sreedev's result, Sreedev did this, Sreedev did that. But that was a start of something, okay? Like they said that thing, and then they say that Rukmini said, let's reparameterize, which I just showed you how ridiculous it is to do. And let's rotate or let's translate, like all kind of creative ideas which I could never think of. And they were arguing with each other, and I was like, why am I even sitting here? Like I should be drinking some coffee or something like that. I almost got the problem. And why should I sit with these two arguing with each other? So yeah, that meeting didn't go well as planned. But I have this really amazing habit. Just a second. So I had this really amazing habit of writing things down on the board. So what I do is that so when you're thinking about a problem, there are lots of thoughts, and things are going way too fast. Like you can't really analyze your thoughts. Okay, so what I try to do is that I try to write them down on a board. I try to write them down on a board without any filter. So if I'm cursing someone, it would be there. Like what the hell is he doing? That would be there. And and then I would freeze my thoughts in the board, and I would look back as a different observer. So that is a great way to analyze my thoughts. And I was doing it, and hopefully it is an estimate. Yes, this is what I wrote that night in ICTS board. I said that our approach is hopeless and we shouldn't do it. So not only that I wrote it, I didn't erase it. So ICTS people did saw it. My supervisor herself saw it, and I received a pep talk in the next morning about how to handle with stress and so on. But yeah. Now, what happened next? So this night didn't went well. And these two people are arguing with each other, okay? And the reason why they are arguing with each other is because they don't think my reasoning is great. And so my imposter syndrome was kicking in. So the only way I can react to it is to come up with a stronger proof, a stronger argument by which they would agree with my case. So I was in the shower and I was looking at the Bonafide PD in the shower, which people don't normally do. But yeah, I was looking at this PD and I was trying to solve it. So you can see that there are a few derivatives, second derivatives at all terms. And or the simplest way to solve it is to make all the second derivatives zero. And one surface which does that is a plane. So you have the plane, and plane have a constant normal vector field everywhere. So plane is an example of a Bonafide solution. Okay. Now is the problem. But the normal is supposed to be this, according to my calculations. So what just happened? I gave a counterexample to my own theorem, which is quite a great achievement to do, because not only the fact that I felt like the stupidest person in the world, now I have to convince my supervisor that I had a stupid idea. Like I have to tell her that it doesn't work because I have a counterexample. So you have to deal with your negative self-talk and negative self-talk from her. And I was worried during that time. So what did I do next? So I presented it to her, and in one particular, we were working on it like crazily. And in one particular evening with Arka, we started doing some things, and we went back to the physics book, and there we saw that they interchanges the variable in one step. And what is the problem with interchange? If you are working in differential geometry, every time you interchange, your transformations better be smooth. If they are not smooth, then you are not in differential geometry. Because in differential geometry, everything is smooth. They forgot to check it because they are physics people. I'm sorry. because they didn't thought that is physically relevant, I suppose. So the solution they gave is not complete. The solutions are only true for which it is smooth. So we have to figure out the full solution. And Arka figured it out, and Arka got this PD. And at every point where it is satisfied, at those points the representation formula they gave doesn't work. So what went wrong? So yeah. At that moment I was thinking like this, like there was absolutely no lesson to be learned from this experience, and there is no point in working it. And this is in the past, okay? This is black and white. If you are watching the movie, so so far everything is black and white. So let's go to color. Let's go to the future for a second, because there were lessons to be learned from this experience. So let me go to the lessons. So in the future, I happened to send an email to Rukmini where I said that I don't have time to, or I can't write GI or TOEFL anytime soon, and I have to finish a master's thesis. So please give me something to read. And then she said that read my Ramanujan identities paper, which is based on number theory. So it was a boring paper, but there was something waiting for me in the last page, which was that she made a mistake in her previous paper. And not only that she made a mistake in her previous paper, here my PD is there. And not only that my PD is there, here she is saying that those fails at umbilical points. Umbilical points means zero Gauss curvature points, okay? So yeah, at zero Gauss curvature points, those PD fail. That is what she is claiming. So now my immediate instinct is to check whether it is true in my case. So I compute the Gauss curvature, and look what I see. My PD is in the numerator. So what did I get from here? So the fact that the PD was satisfied was equivalent to saying that that point had zero Gauss curvature. And what the physics people showed was in fact was that at every non-zero Gauss curvature point they have a representation formula. Nobody did it before, and this was a totally new and wonderful thing. So we added it to our paper, and this is from my paper, and this is a theorem which I stated based on that. So what's the lesson I learned from this experience? Well, there are two things. It wasn't like Arka and Rukmini weren't smart enough to find it. It was like they were too busy doing something else. Arka was attending his IISC lecture because it was summer project and he went back. And Rukmini was in fact checking my paper and dealing with teaching and so on. So they both didn't had any time, which is why it's in my single author paper. And so it had to happen that way. Now I look back because that's the only way I got this result. Otherwise, it would be a it would be a collaborative result. You know what I mean? And I am incredibly what should I say? Incredibly an egoistic person. So yeah, so I wanted this result of myself, and God gave it to me. So that's what I should say. And the second fact is that it's okay to make mistakes in the paper. The only reason which I got it is because my supervisor made a mistake in her paper and had the time to write it down in the last page. If she didn't write it down, then there is no way I'm going to find it. So this is what I have to tell you people who are going to be like the future researchers or the researchers right now. But the thing is that it's okay if you make mistakes in a paper, but you because you would receive at some point of time someone with a terrific amount of imposter syndrome who would go ahead and use it in his paper. So it's okay if you make mistakes. And now let's go back to the story. So this is Arka, and what's happening right now? So I said so many nice things about Arka in the beginning. So you should assume that there is something bad is coming. And yeah, this is what he did. He almost solved the problem using my approach. So you remember that at one night I wrote an ICTS board that this approach is hopeless and we shouldn't do it. So he used that approach to almost solve the problem. And his idea was that since the normal is same everywhere, he find a correspondence between curves and normals in the plane and in the normals vector fields. And using that correspondence, he solved the problem. But there were two things which made me happy in this image. The first thing is that uh, to find FNG explicitly may not always be possible by this approach. That is his imposter syndrome kicking in. But that made me happy because that means that he didn't fully solve the problem. So there is something left to do. And secondly, and this is the most important thing, which is that this while I believe that through speed complex system you will be able to do it. So not only he is telling me that he didn't really solve the problem, he is telling me what to read next. So this is what I wanted to do next, which is to read speed complex numbers so that I can do it before he does. So let's go back. So this is the picture of me in that place. It was that I was feeling like the biggest failure because I started a research which I thought was amazing, and I thought whatever my supervisor and my collaborator was saying was stupid. And then my collaborator went ahead and got a better result, and then I'm standing here. So it's not going well with me. And at this point of time, what happened was that I started reading stuff. And I would show you 3 papers within a short amount of time. I don't want you to read anything, I just want you to show them. So these are 3 papers. One was a time-like minimal surfaces in Lawrence University space. The same problem solved. The same problem solved is for space-like minimal surfaces. And in the third article, uh, we had something from paper of Rukmini Dey. Now here I have a story to tell. So what happened is that here she is claiming that Boniface solutions are exactly same as graphs of surfaces, time-like surfaces over time-like planes. Time-like or space-like surfaces over time-like planes. Okay, so that's what she is saying. But in the proof, she is only proving it for YZ plane. So at a point of time where your advisor is saying something in your theorem, and she is proving something else, you have to do something. And I did the wisest thing, which was to go out to her office and ask her what did she mean here. And she was like, she gave me a terrific answer, which is that she forgot what she did. And not only the fact that she forgot what she did, now she wants me to fill the blank. Like she doesn't allow me to take this theorem, cite her, and present my research. She wants me to fill the blank. So I filled the blank, and she was right. So I got the fact that over over xz and yz planes, graphs over xz and yz planes are in fact Boniface solutions, and over xy case we will get a different PT, maximal surface PT. So I'm going to write it down because this is going to be crucial for the rest part of the talk. This is the crux of my proof. So I had xz and yz. So this is like the most important thing in my proof. And now what she said in her paper, she said that Bonneville solutions are graphs, time-like and space-like minimal graphs. That's what she said in her paper. So this is the plan. This is a big plan which I had, and I like to write plans as well on the board, like when I'm free. It helps me mentally. So what people did is that they solved it for space-like minimal surfaces and time-like minimal surfaces. The problem I wanted to solve was solved for space-like minimal surfaces and time-like minimal surfaces. And what my supervisor showed me is that these are the surfaces which I want to work with are graph-like surfaces of the above kind. Okay, so what do I want to do? Well, I want to solve this problem for graph-like surfaces. That's all I have to do, and I just have to connect a bridge, make a bridge between these two, so that I can understand when is a surface as a graph, so that I can solve my problem, right? So I kept on thinking about it. This was a big plan, and this is going to work. So I kept on thinking about it a lot, and I couldn't do anything. So I did the next smartest thing to do, which was to simplify the problem. So how do you simplify it? You forget the space-like and time-like part. You just ask, can a curve can be included in the graph? So here I have to tell you something about solving similar problems. Solving similar problems may not get back to you on the bigger problem, but it will give you some confidence to go back and do it. Okay, so that's some mental psychology which we use on our research. If you can't solve a big problem, solve a small problem so that you feel proud to do the big problem. So yeah. Now in this problem, I found a curve which can't be inserted any graph, any xy graph, and it can't be inserted because its projection map is not injective. It circles. So in that case, I went back. So I am working with specialized graphs. Okay. So not every curve can be inside a graph to begin with. So why should I ask a question for now for specialized graphs? Because not every curve can be there. So at this point of time, you can do two things, which is to find out all the curves which can be included, or you can ask your advisor what to do next. Because if that is not interesting, then there is no point in doing it, right? We have to get money in the end, so you have to deal with some problem which is interesting. And she said that instead of working with graph-like surfaces now, let's work with locally graph-like surfaces. So I said okay, and I started working on it. And to understand locally graph-like surfaces, I started from what was now. I know that time-like and space-like surfaces over y-z and x-z are Bonneville solutions. Now, what is similar now? So the first step when you're working on a research problem is to Google and find out whether anybody else did it, so that you don't have to do it again. So yeah. So this problem wasn't solved for surfaces, but that was solved for regular surfaces. There was a similar result, luckily. And for regular surfaces, it is always locally a xy, yz, or xz graph. Okay, but I wanted exactly xz or yz graph. So what to do next? Well, I would try to understand, is every surface locally yz or xz graph? It's visually true. Every surface I take is locally yz or xz graph. It's true in general. Nobody solved it. I don't know why they didn't solve it. But because if they had solved it, I just had to cite and I would be done. But that didn't happen. And now what did I do? So this is a technique. So if you want to know on which plane it is going to be a graph, all you have to do is take the Jacobian and look at a 2 by 2 minor. The Jacobian would have a 2 by 2 minor, and whatever 2 by 2 minor is there, that is the plane where this surface would be a graph. Okay. So here in this particular case, it is an xy graph because the 2 by 2 xy minor is non-zero. Now I started asking the question, but I don't have to ask for general surfaces. I just have to deal with the xy case, which is the most weird case. If it is xz or yz, I am done. If I can show that xy graphs are also made up of bricks containing xz and yz graphs, then I am done. So I try to do it, and yeah, this is the question I asked. So I take an xy graph and try to find the Jacobian, right? That's the thing to do. So you find the Jacobian, and then you see that the determinant is exactly same as fx or fy. So the problem is all about can fx and fy can be simultaneously seen. So this is how we went. So this is the part. and now fs and fy can be simultaneously 0. Well, if they are simultaneously 0, that would mean that the surface is locally a constant. Now, if you have some imagination about soap films, it is the fact that it can never be like a plane in a specific location and a smooth surface in another location. That can never be a soap film. So I was like, I almost sold it here. Let me send my supervisor an email. Of course, I don't have a full proof, but nobody cares whether you have a full proof. We'll fill the details later. So I sent her an email, and then the next amazing thing happened. So, yeah. So what happened is that Arka provided a counter example. So he said he showed a surface which is an xy graph, which is not an xz or yz graph. So I was quite sad, like obviously, and he like I can go into the details of the counter example, but again I'm not going to do it because I have too much ego. So let's get into my second approach to attack this problem, because in the specific counter example he gave, the problem points were isolated. So now all I have to do is this always the case? Because then you can just remove those points, right? So that was all I had to do. And luckily I took an MCV course in the last semester. And so what I did is that fx equal to 0 is the null, fy equal to 0 is the null, you study the intersections. And those are like steady states and so on. So I try to find some theory like that. And I try to find out whether it would work, right? What happened next? Well, I went to her office, went to my supervisor's office. I presented my big plan without actually having any proofs in my hand. And I thought that somehow she would believe me. Like, I would give her some cash, or I would actually smile a lot, or something like that would happen, and she would believe that my result is true, and let's submit a paper. So that never happened, but something else happened amazingly, which was that my friend Arka actually find a way out. So I started writing down the nug lines on the board, and as soon as I started writing it, he said that you don't have to do any of this. You notice that the normal is given by this equation. It is space-like, so it should be greater than or equal to 0. That's what space-like means, and it would mean that this sum is greater than or equal to 1. My question was, can fx and fy be simultaneously 0? They can't be, because it is supposed to be greater than or equal to 1. So even though the theorem wasn't true for surfaces in general, it was true for the surfaces which I wanted to work with. So this is another instance where I have to say that you have to be really good. Yeah.
Working on soap films, how did you get to low-efficient surfaces?
Yeah, that's a great question to ask, and I skipped that entire part completely in this show. So what happens is that in Euclidean 3 space, you can study zero mean. So fields have this specialty that they are locally area minimizing, and because of that, they have zero mean curvature everywhere. And this is now a mathematical property. You can study it in different spaces. And if you take a Lorentz-Minkowski space, which you might know as a physics person, so in that space, you can take zero mean curvature surfaces. They could be space-like or time-like, and they are called space-like minimal and time-like minimal surfaces. And they have similar geometry, okay? They can also be studied by complex analysis. And if you change a few signs, you would get everything in minimal surfaces can be changed to everything in maximal, and that's kind of sense. I skipped that part because I believe that everyone thinks math is boring and shouldn't be. Like I didn't want to spend some time there. Now what happened next? Well, I got this result and I could write a paper, but the thing is, no journal would accept it because journals need more results. So what can I do next? Well, I have to find out which curves and normals for which this problem can be solved, right? I know that now regular time-like minimal surfaces are Boniface solitons. Okay, that's another crux of this entire presentation. Now, once I know that thing, my question is, what kind of curves and normals have regular time-like minimal surfaces as solution to the Bjorling problem? Okay, so how can one solve it? Well, I try to solve it, and then I hit my first superb thinking, which was that my superb thinking at that time was that listen, I can take a surface. So by regular surface, I mean topology stress surfaces, in the sense that these are two-dimensional manifold, and this is exactly what a surface, like a topologist imagines when he says the word surface. But a geometer might add some garbage to it, which we call as singularities, and that's what we mean by surfaces. So these are two different terminologies, and regular surfaces just means two-dimensional manifolds. And you can take a non-regular surface, a surface with singularities, you can find a regular curve in it, and since we added some uniqueness aspect to our problem, the solution to the Bernoulli problem should be, for that curve, should be same as the non-regular surface. So if I take a non-regular curve, if I take a regular curve, I might get a non-regular surface as solution. So I thought it is a dead end, we shouldn't work on it anymore, and I forgot it. I forgot it till I encountered this paper. This happened fast forward, like it happens in the future. And I encountered this paper on a particular night where I was searching about this kind of research. I was obsessed with regularity research because that's what makes my paper interesting. And I was searching for research and I happened to find this paper. And here they state something, regular Bernoulli representation formula. I'm working with regular surfaces. So there is something going on. They are taking regular curves here. And they are getting a surface. But whoever the author is, I cursed him a lot during that time because he wrote that he is getting a time-like surface. And he also had a singular Bernoulli formula. So he should be getting a surface with singularities there, right? So yeah, I was almost certain that what he meant is regular time-like Newman surface, but he was too confident enough to not to write it. And so what I did, well, I wrote an email to my supervisor and my collaborator saying great news on the subject line. They said that this paper proves these things, and we are done. Now I just thought for a second after writing that email because my supervisor is not going to accept me without a proof, and I have to go to her office and argue for 3 or 4 hours after this to convince her that it doesn't work. So I have to come up with a proof right now. So at that night I made a draft, and because of I made a draft, I couldn't really sleep. So because I was thinking like, what if it goes all wrong? Because I had all of my expectations on this result, and if this result is true, I'm done. Otherwise, I'm not done. So I was thinking like maybe I should figure it out. I shouldn't like go through this state any longer. It's like expecting a test from someone and they are completely ghosting you. Like you want to end it at the immediate second you get. Either you just completely lost it with that person or like you continue. I don't know. But yeah, so what did I do? So I wake up in the early morning, which I never does, and I went to the board and tried to calculate it. And in the first hour, I got absolutely nothing because everything here was based on PDEs. And I was cursing that authors a lot. And it's in fact the most I have cursed anyone, I believe. So for an entire hour, I was like, why did he have to do this? He just had to write a normal paper and I would have been done. And I don't know how these referees didn't notice it either. Or they might have felt that it wasn't too relevant, but it was relevant to me. So then in the next hour, I realized I went back. So I lied to you in the beginning. No, I didn't lie to you. But the fact that these things are useful. Like we are going on a full circle. This is some slide which I showed you earlier. And you see that here is the velocity. Regular curves means that the speed is non-zero everywhere. So from here you would get that xu is non-zero everywhere. And xv is a normal unit vector field normal cross product velocity. So it has the same magnitude. It is also non-zero everywhere. And if you have two non-zero vectors, tangent vectors, which can be parallel, then that would give you a two-dimensional surface without singularities. This was a proof. So I wrote the email. I completed the email this time and I wrote it down. And my supervisor wrote something back which I still to this day don't know whether she meant it or she just wanted me to encourage me or something like that. But this is what she wrote. She told me that I'm good enough. And then after this email, let me give you a summary of what would happen. You take regular curves and you solve the Bernoulli problem. Then by the result of that paper, you would get a time-lag Newman surface without singularities as solution. And that is always locally x or y z. Because of that, that is the bond if you solve it and locally surface. So this is in fact a section of my paper. And this is not the only section which it has. So this is my paper on archive. and it have these following sections, and there are 4 sections which are important, and I described one section to you, and this is all there in this talk. So what did I do right now? So I described to you a talk where I barely talked about any technical stuff and any math at all, and I gave you a talk where I was mostly venting about my feelings. So I have to tell you why I gave this talk or why I chose to give this talk. Well, it was because of this part which I encountered by Craig Ferguson, which he wrote in his autobiography in some sense, where he says like he's an incredibly rich and charismatic person, and what he writes is that he wants other alcoholic and other people who had similar past before him to feel good because he made it so far and to take similar paths. So that's the entire point of this talk, which was to tell you that if you are hopelessly stuck, or if you are having like a terrific amount of imposter syndrome, or if you are getting stuck, or if you are cursing your supervisor, there is a chance that you will get a paper by the end of it. So thanks a lot for attending, and thank you for this. Yeah, thanks a lot for coming. Okay. I mean it. Yeah, are there any questions or something like that? Yeah, I hope there are no questions.
Thank you all for attending this talk. We hope you enjoyed.
Thank you.
Amazing. Thank you.